Assalamualaikum warahmatullahi wabarakatuh. So we are from Group 10 and we will present about the assignment 2. Okay, for introduction, so the problem is traditional manual KYC is labor intensive and error prone. So our solution is optimization via automated deep learning object detection. So design a real-time facial authentication system using a YOLO architecture. So for our data source, model trained using facial image from UTSM student metric card, and then the result enable live identity verification to accurately identify and classify team members. So let's look at the next slide to discuss our dataset collection. So for our assignment 2, we will use 5 dataset collection and 20 set of picture for each of it. For dataset collection framework, the objective is designed for high fidelity identification targeting 5 selective individual. So for the source, initial facial imagery was extracted directly from mutation to the metric card. And then environmental introduced variation in distance and document orientation to replicate real world unconstrained identification scenarios. So for the structure, use multi-image acquisition per participant to maximize model generalization and prevent overfitting. So for our dataset preparation, annotation manually annotate using RoboFlow Polygon tool to draw precise bounding boxes around facial regions. So localizing and formatting boxes were mapped to specify identities and all images were standardized to a fixed resolution for a YOLO compatibility. Mutation apply geometric rotation plus minus 7 degree and plus minus 90 degree and saturation shift plus minus 25% to simulate diverse real-world card positioning and lighting condition. So for our dataset split, maintain a total of 96 image split using a strict 70-20-10 ratio, resulting in 67 training, 80 validation, and 11 testing image for a perfectly balanced class representation.
So next is on the results. So for validation between YOLO V11 and also V26, YOLO V11 demonstrate robust class-wise accuracy by correctly identifying each target, which is a perfect 5 over 5 diagonal classification for AFID. So as for YOLO V36, it failed to generalized and completely missed Arif in all 5 accuracies by misclassifying him as background, a direct result of over-optimized weight that caused model overfitting. So next is about position breakdown. YOLO V11 outperformed YOLO 26 with higher overall MEP of 0.918 compared to 0.881. However, both models struggle significantly with RF, which yielding their lowest individual score at 0.678 for YOLO V11 and also 0.551 for YOLO 26. This proven that highly similar facial features made RF the hardest classification boundary in the dataset. For the net result is the threshold optimization. So YOLO V11 achieved a peak F1 score at 0.83 at a 0.374 threshold, while YOLO 26 peaked lower at 0.74 at a 0.347 threshold. This proved that the default 0.5 development threshold was suboptimal and that resisting to this curve optimized value is required to maximize the interference performance. Next in result is the comparison between both model, which is model 1 YOLO V11 and model 2 YOLO 26. So for the model selection between efficiency and also accuracy, So for efficiency is YOLO 26 because faster interface between 14 millisecond and also 17 millisecond with fewer parameters and also lower computational complexity. So for accuracy is YOLO V11, which achieves superior MAP, a higher F1 score, and more reliable face recognition during live webcam testing. So in conclusion, for model selecting is YOLO V11 is selected for practical KYC deployment due to its superior real-world authentication, accuracy, and also reliability. So in final development verdict, for YOLO 26 Advantage, it demonstrates how stable training converge during the initial development phase, while YOLO V11 Superiority outperformed YOLO V26 across all critical metrics, including MAP 50, precision, recall, and also interface speed. So in selection, we also select YOLO V11 for practical KYC development due to its superior quantitative metrics and also reliability to real-world live webcam performance.
So the next slide is real-time application. First of all, the testing environment, we use both model. Uh, we deployed both model using Google Colab and evaluated via real-time webcam stream to test the KYC face authentication capabilities. So for the YOLO V11, it demonstrated highly consistent face localization and robust identity recognition, such as by detecting leaf key with 0.5 to 0.9 detection. For YOLO V26, uh, although it have strong validation scores and better computational speed, it suffered frequent real-time detection and identity misclassification. So from that, for this project, we choose YOLO V11 as the optimal architecture for proposed KYC system due to its superior reliability under practical field condition. Uh, Next, the analysis of accuracy degradation. So for both model, the difference in accuracy between validation and live webcam can be associated with the issue of domain shift in the case of the dataset and deployment environment. So the training image were acquired from ID photos of student through a smartphone camera, where the inference phase was performed via webcam, where there was some variation in the light setting and viewing angle of the image. Next is the dataset limitation. So the small volume or the small total image of training uh, restrict the model from learning adequate variation in facial appearance, image quality, and posture. So the last is unconstrained environmental variable. Uh, The variation of lighting condition, pose of the face, and the distance from the camera between the training data set and webcam test environment may have also been a source of the decrease in accuracy during testing. The image that were used in the training phase had been obtained under more controlled conditions, but the environment in which the webcam was placed varied with respect to shadows, lighting changes, and head movement. So this variation may have affect the way the face appear visually and thus affect the accuracy of the model, the model system. So next slide is the picture of testing the model in real time. So as shown in the top left frame, YOLO V11 successfully detect the Rifki phase, establishing a stable bounding box with a height confidence of 0.76. However, if we look at the top right frame for YOLO V26 model, it completely experienced a left failure mode. The output uh, Its output is a blank frame, which is it can detect the person uh, for this model and failing to register or detect any human within the camera viewport. So the second picture, which is Arif, in the bottom left frame, Euro V11 demonstrate robust identity recognition, identifying Arif accurately with an excellent confidence score of 0.88. Conversely, in the bottom right frame, YOLO V26 introduced a critical discrepancy. Instead of recognizing Arif, it misclassified his face entirely, assigning uh, a wrong label of Afiq with a confidence of 0.62. So this visual evidence clearly showcases that YOLO V11 maintains the superior classification accuracy under real-time constraints. So we moving on the next slide. We continue with the subject Haziq. So if we look at the top left, the YOLO V11 show the minor classification error by tagging Haziq as Arif with confidence 0.51 confidence. So however, when we look at the top right, the YOLO V26 also suffered the exact same misclassification, labeling him as Arif. So this indicate a highly similar facial feature boundary between these two individuals that confuse both networks. So the next subject is Hamizan. So in YOLO V11, uh, the output logs onto Hamizan face, but again, misclassifies misclassification made him detect as Arif with confidence 0.87. Similarly, with the YOLO V26, duplicate the same error. So misclassifying Hamizat as Arif with 0.7 confidence. So this visual discrepancy on this slide perfectly illustrate the domain shift phenomenon and dataset size limitation. So that I mentioned earlier. So because our training dataset was exclusively sourced from static smartphone photos of student metric cards, the models lack exposure to varied live environment. So when subject to unconstrained real-world variables such as the specific room shadows, webcam viewing angle, and physical background noise, uh, may affect the performance for both model. So because YOLO V26 completely dropped the droplet detection or cause critical cross identity failures for the first two subjects, YOLO V11 remains the structurally superior and more reliable choice for our KYC architecture. So for the conclusion, the project successfully implemented a KYC facial authentication solution for 5 target identities using YOLO V11 and YOLO V26 architecture. Quantitative evaluation revealed that YOLO V11 significantly outperformed the YOLO V26 across all key detection metrics, achieving an exceptional 0.981 MAP alias zero point 0.5, 0.915 precision, 0.952 recall, and 0.83 F1 score. Conversely, while YOLO V26 offer reduced computational costs, fewer network parameters, and highly efficient processing speed on paper, it failed to deliver under live webcam deployment constraint. It introduced frequent real-time detection, dropout, and critical cross-identity misclassification. So this performance divergence highlight an essential research insight, such as validation metric alone cannot serve as the sole predictor of practical efficiency. Real-world computer deployments are heavily susceptible to the domain shift phenomenon, where shifting illumination profile, dynamic shadows, facial posture, and restricted training sample size can actively degrade an overfitted model. So, final model that our group choose is YOLO V11 as the optimal architecture for proposed KYC system due to its superior real-world accuracy and robust tracking stability under field condition. As future work, we plan to actively expand our custom database by increasing both the overall dataset size and the environmental diversity of our sample. So this will allow our next generation intelligent control model to learn highly unconstrained facial features and completely eliminate domain shift vulnerabilities. So with that, we conclude our group presentation. So thank you very much.